All right, welcome to our next lesson. We're going to talk about 6.2, homogeneous linear equations with constant coefficients. Okay, so these are equations of this form. So these are equations of the form. Let me zoom in there. A sub n, y to the n, so this is the nth derivative of y, plus an minus 1, the n minus 1 derivative of y, all the way down to a1 y prime of x plus a0 y of x equals 0. Okay, so let's take a look at all these terms. Constant coefficients, that means that these a's are just numbers. Okay, those are just numbers. Okay, homogeneous or homogeneous, that means that your equation is set equal to 0. Okay? Okay, so the first thing that we're going to do is we're going to go ahead and we're going to define what's called an operator. Okay, so we're going to define L of y to equal, for this situation, a sub n, y to the n, put an x on there, plus a sub n minus 1, y to the n minus 1 of x, all the way down just like we had before. Okay, now if I'm really being particular, and I should be, they don't do this in the book, but if I'm really doing this right, I would put like an X there. I'm putting it in red just so that you know, it's just my own problem. Okay, my own little OCD about being mathematical. Okay, but I want to put it there. Okay, so just like we did, this is very similar to what we did for second order equations. Okay, now all we're going to do first is we're going to make a guess. Okay, and our guess is L of e to the rx. Okay, L of e to the rx is going to equal a sub n r to the n plus a sub n minus 1 r to the n minus 1 plus a sub 1r plus a sub 0. Now, I didn't forget about the e to the rx. That's still there. Okay, and so our equation is L of e to the rx equals 0. Okay, I guess I don't need the x here as much as I thought I did, because we have the x dependence is inside of the y here. Okay. Okay, now one more thing and then we'll start doing some problems, okay? Or two more things. First, sometimes we write this as L of d acting on y of x, where d is d dx. Okay, so basically what we're doing when we talk about it in that way is we say a sub n, the nth derivative of y, plus a sub n minus 1, the nth minus 1 derivative of y, all the way down to what? A sub 1, just the derivative of y, plus a sub 0, y equals 0. Okay. And then this thing, this polynomial we have, getting tired of writing it, okay, we call that the characteristic polynomial. Okay, so effectively for these linear differential equations with constant coefficients, what this problem comes down to is a college algebra problem of factoring a polynomial. Okay. Okay, just like it did for the second order equations that we saw, I think probably last week. Okay, so just like there's actually three different things that could happen. Okay, so we have three possible situations. One, everything's good. We've got all real distinct roots. Okay, so if that happens, then our solution, our general solution, is y of x is c1 e to the r1x plus c2 e to the r2x plus cn e to the rnx. Okay. Second thing that could happen. Maybe we have a repeated root, or we have a root that has maybe even up to m times, okay? So a repeated root of order m, where m would be less than n. Well, less than or equal to n. Okay, we could have multiple repeated roots, of course, but let's just go with one for now. Okay, and then you can see how it'll work for more than that. Okay, so if you have that, then what you're going to have is that your y of x is going to be c1 e to the r1x. Okay, let's imagine this one is the repeated. So let's pretend r1 is repeated in this world. Write that down here. Okay, plus c2x e to the r1x again. And you're going to have r1 up to m minus 1, x to the m minus 1, e to the r1x. Okay, and then you're going to have the other roots. Let's call this e to the r2 of x, and then plus cn e to the r, I guess that's going to be n minus m of x. Let me write that better. There we go. Let me write that again in there. There we go. Okay. And then the third thing that could happen is maybe we have a complex root. Now, complex roots come in pairs. Okay. Okay, so if you have a complex root, then you're going to have, let's say it's R1. Okay, so you're going to have y of x equals c1 e to the alpha x cosine beta x plus c2 e to the alpha x sine beta x plus, let's say that's c3 e to the r2x plus c4 e to the r n minus 1x. Okay, so those are the three basic things that could happen. Now, you could have a repeated complex root, which we'll look at in an example later, but it does exactly what you think it does. So if you have a repeated complex root, the next one would be, plus c3x e to the alpha x cosine beta x plus c4x e to the alpha x. You get the picture, okay? So we'll do an example like that. So that's basically the rundown of the theory. So I am going to put, I've put, by the time you've seen this, I've put some videos on how to factor polynomials as well in case you need a refresher. Those I took from my college algebra class, but you're welcome to use them. You may need them if you want to remember how to factor polynomials. Okay? All right, I'll see you in a new video shortly.